Okay, so let's get started today with our warm up. So in the chat, what I want you to do is I want you to. Am I doing this one? Come on. Am I sharing the right thing? I think okay. Okay, so in the chat, I want you to write down what you think you used the most energy for yesterday. So what do you think you used the most energy for yesterday? What do you think? You taking a test. Oh, that's funny. That's funny. What do you think you used the most energy for yesterday? Taking a test. What did I use the most energy for yesterday? Getting out of bed, probably. What do you think you used the most energy for yesterday? Is there a correct answer? No, there definitely is not. But it could be. There could be a correct answer. Sleeping. Sleeping is, you actually use a lot of energy while you're sleeping. I don't think people know that. Your body actually burns a lot of calories when you're sleeping. That's because when you're sleeping, your body has to do all the repair of all your muscles and stuff. And how's it going? When you sleep, so during the day, right, what you guys do is you guys watch TikToks and whatever, and then your brain like gets destroyed and you lose all the brain cells in the few brain cells you have, you lost it all watching TikTok. So when you sleep, your body has to repair and add new brain cells. So, when you have two brain cells during the day and you lose both of them watching TikToks, when you go to sleep, your brain adds two more brain cells for you. So, yeah, it needs energy to do that, believe it or not. Probably using a computer. Computers use a lot of energy for sure. Let's get some more responses here, y'all. We only have like 3 or 4 right now. What do you think you used the most energy for yesterday?
How's it going, Mr. Who?
How's it going, John? What do you think you used the most energy for yesterday?
Catching.
Catching. Oh, nice. Great.
Oh, I used a lot of energy when I was like breathing pretty hard when I got hit in a place where I didn't want to get hit.
Okay. Did you guys play yesterday?
Yeah, we were away though.
Okay. Breathing, catching, exercising, these are all good ways of using energy. Some people are very tongue-in-cheek today. That's cool. That's funny. We'll take another minute or two. What do you think you used the most energy for yesterday? Believe it or not, you used the most energy for being alive. That's definitely true. Believe it or not, your brains used most of the calories. Mr. Who, I almost hit a dinger for you. Oh, but you didn't. So that's disappointing. So that's good. That's a shame. I think I might have saw that one on Tuesday. Let's take one more minute. What do you think you used the most energy for yesterday? Thinking and just being alive. Yeah. Your brain uses most of the calories in your body. So my practice for what? Practice for what? Lacrosse? Oh yeah, I've seen those lacrosse practices. Yeah, those seem like they burn a lot of energy for sure. Um, okay, so what's the correct answer? I don't. Oh, taking a nap. Ah, great. That reminds me, I should take a nap right now. Sorry. Next later today. Um, keeping your body temperature up. Yeah. Keeping your body temperature up. Your body has to use a lot of calories for that, for sure. So what are we going to do today? We are going to be talking about energy, if you believe it or not. So if you want to, you can fill out a graphic organizer to help you take notes. If you want to take notes on your own, that's also good. If anything, if that's preferable, it's good to practice taking notes. But if you're not good at taking notes, you can also just fill this out as we go along. So yeah. So okay, and then if we have time, I added a new section for Roller Coaster Tycoon relates to energy. We should have time. We should have at least 20 minutes at the end of class to work on that. Okay, so okay, so let's talk about energy. So what is energy? Energy basically refers to the ability to create change, essentially. So what it actually is, it's basically measuring how much it's basically measuring how much ability do you have to create change. So you can actually measure how much energy you have. You might say that something has 100 something of energy, 1,000 something of energy. So it's actually measurable how much energy something has. What you can do with that energy is you can store it for later use, or you can sort of, you can store it for later use. You can also use it to make something move. Energy can be moving. Example, vibration is a good way of seeing how energy can be in a moving object. But basically, energy is basically the ability for something to create change, and you can measure how much that ability is. What you can do with that energy, you can store it for later. Example, like in a battery, or energy can be moving. So like in a moving object, like a truck, would have moving energy. Vibrating guitar might have moving energy. So there are multiple different forms of energy, but basically this is what energy is and what you can do with that energy. What the key thing is, it is measurable. A lot of the times you might say something like, I feel like I have no energy, I'm really tired today. Well, you can technically measure how much energy your body has. It's actually technically true. Maybe difficult, but that's technically true, which is what we work in physics. We work in the technically trues. Okay, so what do I mean by energy can create change? So here are some of the things that you can do with energy to create change, or we sometimes call creating change, quote unquote, doing work. So that's a special term, doing work. So which we will learn about, I think, later on. Basically, some of the things that you can do with energy is you can change the temperature by heating or cooling something. So if you are baking cookies, you are heating it up, so you're using energy to do so. If you are freezing a popsicle, you are also changing the temperature of it by cooling it down, which means you have to use energy to do so. So if I want to cool or heat something, I will use energy to do so. I can also change the state of an object. So I can turn it from a liquid to a solid to a gas. When you do so, the atomic structure of it will change, right? So generally, solid objects have their structure very compact, really dense, so that the atoms are not freely moving. When they go into liquid, those particles are freely moving. And then when they go into gas, they really truly have freedom of movement. Why does it cost energy to cool something down?
I can try to.
Because objects have a baseline, like there is like an ambient temperature essentially. So if you want to cool it down, you have to apply energy to do so. Like that's why your refrigerator uses energy, because it has to use energy to, you're creating like an artificial environment where all the particles and all your food are moving slower. So you have to use energy to do so. Like otherwise, like everything wants to remain at the ambient temperature of the environment, right? It doesn't cost energy to leave things at the ambient temperature. To cool something down, well, usually when I mean cool something, we usually mean in terms of like a refrigerator or like the air conditioner. If you like leave like, I mean like if you leave like, if you leave like your, like if you just left something out at night and then that got cooled down, I mean that technically does, like if I think this usually, what we usually mean is like, if you're actively doing it. Yeah, I think that's what I think that is. It's like if it's being actively heated or cooled, then it requires energy to do so. If you want to just leave it as at the ambient temperature, it doesn't really require anything to do that. If you change the state of an object, it also requires energy to do so. You're changing the atomic structure of it. So yeah, those are some things you can do with energy. What you can also do with energy is you can also change the volume of an object. So you can blow up a balloon. When you do so, you're actually using energy to do so. You can crush a piece of paper, which also involves using energy to do so. Probably the most prominent way you see energy being used is when you build or you destroy something. And that's because you are changing the structure of it once again. So when you build objects, when you build something, you are changing the structure of it. You're building something together. When you're destroying it, you're also changing the structure. So it basically, if you want to change something, you require energy to do so. When you The last way I guess we can think about energy being used the most is when you make something move or you make something stop moving. So to make something move, it's basically like you are essentially like, you know how when we talk about like when we talk about forces, it doesn't require any force to just like not do anything to an object. But if you want to start an object, you have to apply a force to it. Or when you apply a force to it, you are using energy to do so. So you have to use energy to make it move. When you want to make something stop, you have to apply a force to it to make it stop. And to do so, you're also using energy. If an object was just moving and you just wanted to just let it keep moving, it wouldn't require energy to do so. It requires energy to change the motion of it, essentially. So basically, I guess what the way you can think about it is that whenever there's a force involved, there is an energy involved. If there's no force being involved, then there wouldn't be energy involved. Um, So in terms of how you can use energy, you can sort of speed up a vehicle or stop it. Though that's two good ways of changing the motion. You can also take energy to make the vehicle turn, right? Once again, you're also changing the motion of the object. So basically, anytime you change the motion of an object, you are using energy to do so. The energy from doing this is usually obtained from some sort of fuel, like gasoline or something else, but usually it requires some sort of fuel to do so, to get that energy from. You yourself also need energy. That's because when you're born, you haven't started lifting yet, so you're not very yoked. So when you grow up, you need energy to do so. Right? You have to get energy to make your bones bigger, to make your muscles bigger. So you need energy to change the structure of your body. You also need energy to make yourself move. So if you don't want to move, you don't use energy. If you want to move, you have to use energy. Whenever you get hurt or your cells wear out or they die, because your cells die naturally, you need energy to heal or grow new cells. So this is basically what happens when you watch TikToks. You destroy all your brain cells in your brain, and you have to regrow new cells. Yeah, as you can tell, I have very strong opinions on TikTok. That's the one biggest difference between my generation and your generation. TikTok, Gen Z. And like so, where do you get all your energy from? You get all your energy from your food. Yeah, pretty much. TLDR, food. Food is good. Eat food. If you don't eat food, life's gonna be very rough. Um, so basically, if you want to do something, you need energy. If you don't want to do something, you don't need energy. So do energy, don't no energy. Pretty simple. Um, in terms of how we measure energy, we usually use the unit joules. This is not the joules that you are probably used to in some or heard of in some way or another. This is the more socially responsible joules. Spelled Joules, not the other way. So this is the metric unit for energy. This is the unit that we all use to measure energy. If you want to know what a joule is in terms of other units, it's equal to 1 kilogram times meters squared divided by seconds squared. So this is helpful if you want to know how to convert something into joules. In general, if you work with SI units, so if you keep things in standard units already, so like meters per second, kilograms, if you keep everything in those units, you don't really have to worry about conversions. However, if you're like multiplying kilometers with grams, you may have to worry about conversions, and this is where it might be helpful to know what a joule is actually equal to. It's also equal to 1 Newton times meters. If you're working with force and distance, it's also equivalent. There's also other ways of measuring energy. You've probably heard of something called calories. So calories is used to measure energy, and that's usually measuring energy in food. You also probably heard of something called kilowatt hours. That is usually how you measure energy usage in appliances. So those are all different measurements of energy. But the only one we really need to know in this class is joules. Joules is very important. So there are 8 different types of energy. We're going to cover all 8 different. There are more than 8 different types of energy. There are lots of different types of energy. We're going to cover 8 different types here: kinetic, thermal, radiant, vibrational, gravitational, chemical, elastic, and electric potential. So those are the 8 different types of energy we are going to cover in this particular class. Out of these 8, the 2 most important ones you need to know 100%, very, very, very much, is kinetic and gravitational energies. The others you should know as well, but kinetic and gravitational are the most important ones we're going to use in this class. So if you don't know them, it's going to be very challenging. Yeah, so you should definitely know what they are. We will figure out how to calculate those, I think, in maybe next class or the class of that. But for now, we're going to be going over more of a qualitative description of these energies. So what is kinetic energy? Kinetic energy is the energy an object has due to its motion. So basically, if I am moving,
I can't see your slides anymore.
Oh, thank you. Thank you for letting me know. There we go. Cool. Okay, so the kinetic energy is the energy an object has due to its motion. So if it is moving, it has kinetic energy. If it is not moving, it does not have kinetic energy. If it has kinetic energy, the amount of kinetic energy an object has is determined by 2 things: the object's mass and its velocity. So the more mass an object has, the more kinetic energy it has. The more velocity it has, the more kinetic energy it has. So if you get hit by a bowling ball versus if you get hit by a ping pong ball, the bowling ball will hurt a lot more, I think, last time I checked. If you get hit by a baseball versus if you get hit by a paper airplane, the baseball would hurt a lot more, I think.
Yes.
So yeah. Yeah, big things and fast things have a lot of kinetic energy, thus they hurt more. I like to energy. I use a lot of hurt analogies. Okay, so in the chat here, I want you to give an example of an object that has kinetic energy. I heard some really interesting ones in first period yesterday. What are some things that have kinetic energy? What are some things that have kinetic energy? A Nerf gun bullet. Yes, a Nerf gun bullet does have kinetic energy. Cars. Wow. Wow, cars do have kinetic energy, believe it or not. What other things might have kinetic energy? Are Nerf gun bullets and cars the only things in the world that have kinetic energy? Humans.
A baseball.
Wow, no way. That's so cool. Humans have kinetic energy too. What other things? Dolphins. Wow, dolphins. That's very specific. Someone must have been thinking about dolphins. Baseballs. Yes, baseballs definitely do have kinetic energy. Dolphins do have kinetic energy. Raccoons kinetic energy. The thing is, you consciously had to have thought of like you must like in your brain like that was the first thing you thought of, like raccoons, ant colonies. Okay, now we're just like going into like the animal kingdom. Okay, like sloths. Like what do we do? Platypuses next. Like I don't know how we went into the animal kingdom so quickly. Anything that moves. Wow, it's a really great definition. Anything that moves is kinetic energy. I feel like you just stole it from everyone. Sloths. Wow, like the anything that moves, like the falling respect for humanity. Oh, been there, been there. That is great example of kinetic energy. Sloths, elephants, cheetahs, lions. Wow. Frogs. Okay, now you're just showing off all the animals you know. Frogs, pigs, boars. The Earth has kinetic energy. Yes, the Earth. Mr. Who? Wow, that's a great way to get extra credit. Me, you have kinetic energy apparently. Cool. Erupting volcanoes. Oh. A president of the US has kinetic energy. A bullet does have kinetic energy. There's a lot of things that have kinetic energy. Wow, so many great examples here. Wow. A dog. So how did you think of a frog before you thought of a dog? That just makes, I'm questioning your choices in life. Okay,
The first animal I thought of was a sloth.
You thought of it? Okay, well, I actually said sloth first. So you just,
Oh,
that's called
maybe that's how I
plagiarism.
thought of it.
That's called plagiarism, and that can get you in big trouble. So
I'll
I
cite my
verbally said it.
sources.
It's recorded on YouTube too. So be careful. A wrecking ball, huh? Interesting. Maybe there's a picture of a wrecking ball on the screen. Very interesting. Bacon. I don't know if bacon has kinetic energy. A loaf? Alive. Alive bacon? That's called a pig. Okay. All right. I get it. Rising bread. Rising bread, if the bread is in the process of rising, it would technically have kinetic energy. Yes. Okay. Yes, I get it. You guys are very excited. That's good. Bacon has kinetic energy when it's alive. That's true. Okay. Water falling does have kinetic energy. Okay. You guys are too good. Okay. So now we're going to talk about thermal energy. So thermal energy is created by the random vibration of molecules. So basically, in any objects have a lot of molecules. You're just like naming off every more animals, but go ahead. I won't read them right now, but I will read them later on. Okay, so all the molecules in an object, they're vibrating all the time. And so that amount of vibration is, we actually can measure that, and now it's called temperature. So when we measure the temperature of an object, we're basically measuring how quickly are these molecules vibrating. So basically, hotter molecules have more thermal energy, so they move and they vibrate a lot faster. Cooler molecules have less thermal energy, and thus they move and vibrate a lot slower. So basically, if the temperature is really hot, the molecules are vibrating really quickly. If the temperature of the object is really cold, it's going to be vibrating very slowly. So in the chat, I want you to give an example of an object that has a lot of thermal energy and an object that has very little thermal energy. Okay, now I'm going to finish reading all these animals and stuff that someone just came up with. Bird, worm, ant, salamander, butterfly, crane, eagle, pigeon, hawk, plane, helicopter, or fly. Okay, that's enough. Okay, no. Okay, so panda. Okay. We're gonna go to thermal energy now. Okay, so ice does have. I think I would say that ice has low thermal energy. I wouldn't say that ice has a lot of thermal energy, but I think ice has a very low thermal energy. Lava and ice cream. Great, that is true. Lava does have very high thermal energy. Ice cream has very low thermal energy. High thermal energy is apparently Mr. Who. I do have a lot of thermal energy. Low is water. Water can have a lot of thermal energy if it is boiling. But yeah, I sort of get what you're saying. The sun has very little thermal energy, very little. And the sweet abyss of space is obviously, space is very warm, right? Very warm. Yeah, those are good examples. Hot chocolate versus ice. So I would say hot chocolate is a good example of low thermal energy. Definitely. Something that is ice, like ice cold, definitely has a lot of thermal energy. Great examples, guys. You guys really nailed it. Any other examples? I'm going to give you one of my favorite examples. So an object that is hot, that has a lot of thermal energy, is my new mixtape. Thank you for laughing. Nobody in first period laughed, and they gave me like a very delayed, like, haha in the chat. It's funny, right? Because it's like I'm musically talented. I was an aspiring rapper. Thank you.
I get it. You'd be a great rapper, Mr. Who.
Yes, I don't know if I ever told you, but when I was like a freshman in high school, when I did cross country, me and my friends, we would go on a run, and then we would do these really crappy rap battles where it's like, yo, you're
Mr. Who. We should have a class rap battle, and whoever wins it, gets extra credit.
Wins a rap battle, gets extra credit. That's funny. That's funny.
During our
Maybe
final
it's really
period,
good.
you should show us some of your raps.
I should show you some of my raps. Yes. So someone in the first period requested that I feature on one of his friends' songs. They were like apparently coming up with.
Oh
so they wanted
yeah,
me to feature on it. So yeah, that's definitely going to happen for sure.
nice.
0 degrees Kelvin has no thermal energy, and more than that has some. Yes, that is correct. That is the definition of thermal energy. Correct. Okay. So the next type of energy we are going to just call is radiant energy. Radiant energy is basically energy that is carried by electromagnetic waves. What an electromagnetic wave is, it's literally just light. Light has a electromagnetic spectrum where there are a lot of different waves, but they're all light. It's just that like there's different kinds of like light essentially. So what makes these waves special is that they are pure energy. A lot of the other types of energy will sort of require some sort of mass behind it, but this is just pure energy itself. There's no mass required at all. The amount of energy in these electromagnetic waves is dependent on their wavelengths and frequencies. So light that has a low wavelength and has a high frequency, those have high energy. So like X-rays, gamma rays, UV rays, those all have low wavelengths and high frequencies. So they have a very high energy. Light that has high wavelengths and low frequencies have low energy. And these include microwave, radio waves, and infrared rays. So those are all low energy. High energy stuff like X-rays, gamma rays, and UV rays, these are all high energy, so they're all very damaging for your bodies. So if you spend too much time in UV radiation, you can get skin cancer. When you have X-rays, you usually wear lead plates, like a lead thing over your body to shield you from X-rays. With gamma rays, if you want to know about gamma rays, you can just watch the TV show Chernobyl, and then you will see what gamma rays does to your body. It's very disgusting. I feel really bad for those people. Like they're really brave, but man, one guy on Chernobyl, his like hand just like fell off essentially. It was really gross. Yeah, gamma rays are bad for your body, so don't mess up your nuclear reactors. That's the lesson for today.
I thought that made you into the
nuclear
Hulk.
reactor at home.
Don't they make you
properly
into the
shielded.
Hulk though?
Sorry.
Don't they make you into the Hulk?
They make you into the Hulk. Okay. So that was that. So I can't. So as a science teacher, I can't endorse that. I can't endorse trying to shoot gamma rays at yourself and hoping that you turn into the Hulk. I can't endorse that at all. You can try though. I mean, you shouldn't try, but if you wanted to try, that's your own prerogative. It's a free country. Okay. So the thing about radiant energy is it's present all the time because you can't escape light unless you're in a black hole, but you can't escape light. The suns and stars give off a huge amount of radiant energy, so you can pretty much always see radiant energy day and night, believe it or not. So in the chat, I want you to give an example of an object that emits radiant energy. What kind of object emits radiant energy? Mr. Who? Wow, that's a very common thing. Apparently, I also emit radiant energy. That is true. That is true. Bonus points if you can figure out what kind of radiant energy I would emit. A microwave. Why would a microwave emit radiation? Maybe because there's something called microwave radiation. Interesting. Light bulb. There we go. Bingo. Light bulb's a great one. The sun does emit radiant energy. Godly radiant energy. That's yes. MRI. Yes, MRIs do use. I'm not sure what MRIs use, but MRIs definitely use radiant energy for sure. My brain's radios, long string. What energy does your brain emit? The thing is, that assumes your brain has any sort of thing in it. So if your brain has no energy in it, which for a lot of you, that's definitely true. Your brains wouldn't be emitting energy. So I'm
Hey. My brain has a lot of energy.
I know. Yeah, don't worry. I believe you.
That was intended towards like James, not me.
That's funny. Long, strong wavelength. I don't know what that means. Computers do emit wavelengths, do emit radiant energy. What do they emit? I'm not actually sure, but they definitely do. Any object with warmth, just because sometimes you can't see it. Yeah, any object with warmth, that is just because it emits radiant energy from Mr. Who. So yes, any object that has a temperature emits infrared radiation. So our eyes can only see visible light. So I actually didn't include visible light in here because that's like in the middle. But visible light is a type of electromagnetic wave. But that's the only kind of stuff our eyes are sensitive to. So at night, when there's very little visible light, that's why infrared, like night vision goggles and infrared stuff are there. It's because those pick up on infrared wavelengths, and you can use those to see it. So very cool stuff. Okay, so great ideas for radiant energy. The next kind of energy that we're going to talk about is vibrational energy. So basically, what happens is when you talk, when you're talking, your air is coming from your mouth and it's slamming into all these molecules back and forth, back and forth, back and forth, back and forth. Is you're carrying this vibrational energy through what we call sound. So basically, it's literally just like energy that's being passing through molecules because the molecules are just slapping into each other, they're hitting each other, and then they're carrying the energy through that. So which is why if you heard the phrase, no one can hear you scream in space, that's because in space it's a vacuum, so there's no air. So when you say something, there's no air there's no air for you to pass the sound through. There's no molecules that's coming out of your mouth. It's not going to slap into something and then carry that sound through. So yeah, so if you're ever in space, no one can hear you scream. Very, very morbid. So once again in the chat, I want you to give an example of where vibrational energy can come from. Mr. Who's voice, you have that ready to go. Okay, I see. Actually, now we're just picking on Mr. Who. I see how it is. What are some other examples of where vibrational energy can come from? Where can vibrational energy come from? Speakers. Yes, they can come from speakers. Music, instruments. My mixtape. Oh, someone remembered that. Bonus points for you. Music. Yes, music could have a vibrational energy. Instruments could have vibrational energy. Anything else that might have vibrational energy? Footsteps. Yes, footsteps can have vibrational energy. If you are like me, I have very loud footsteps. I once got called out by someone who was really upset that I was like slamming my feet on the floor. And that actually made me really insecure about my walking for a few days.
It's because you're too strong.
Yeah, it's definitely because I was too strong. Yeah, for sure. Yeah, definitely true.
Just tell them strong steps for strong boys.
Makes no sense at all. Sure. Whatever makes you happy. Okay, so yes, those are also good examples of vibrational energy. Any last minute examples of vibrational energy? Okay. Gravitational potential energy. So this is probably one of the most important energies that you need to know. And that's basically the energy an object gains when it's lifted into the air. Lifted into the air is like probably a misnomer, I guess. It should really just be anytime an energy is sort of technically above sea level, I guess. It's anytime it's elevated. So for example, on our top of a roller coaster, it would have a lot of gravitational potential energy because it has elevation. So the idea is that if you lift a pencil in the air and you let go of the pencil, it'll start to fall. That's because when you lift the pencil up, you're essentially using energy and you are storing the energy into the elevation of the pencil. So when you let go of the pencil or the pen, all that stored energy that you use to lift the pencil or pen up, it's going to turn into kinetic energy as it falls. So you're basically storing energy in the object through its height, and then when you release it, all that potential energy gets converted into other kinds of energy, usually kinetic energy. So basically, anytime an object is elevated, it has potential energy. The thing about the gravitational potential energy is how much an object has depends on its mass and height. So if you have a very big object, that's going to have a lot of gravitational potential energy. If it's very tall, it's going to have a lot of gravitational potential energy. So basically, tall, big objects have more gravitational potential energy. Light and low objects do not have a lot of gravitational potential energy. If an object is technically resting on something, it would technically really wouldn't have any gravitational potential energy. So we're really looking at sort of the elevation above something, essentially. I guess one thing that I guess I should also sort of, I guess I don't know if I wanted to. I guess what I could say right now is that you can define like any surface as having. So it's like the thing like potential energy is all like relative essentially. You're all comparing it to a relative elevation. So I could say that that this table has zero gravitational potential energy, and then I lift a pen and comparing the potential energy of the pen to the table. I could also say that the ground has a zero potential energy. I'm comparing the elevation of the pen to the ground. So it really just depends on what you are comparing the elevation to. Yeah, that was one thing. I could ask you for an example of gravitational potential energy. I could ask you for one, you don't, but I don't think I'm going to because I think it's pretty self-explanatory. Okay, so chemical potential energy. This is energy that is stored in the molecules of materials. So it's basically fuel. Basically, the structure, how would it work if you took two equally massive objects in space with no other forces? Okay, so this is where, okay.
Like, what would be based off of what?
It actually wouldn't matter. It would actually be the same. So, okay, so from, I guess you can think about, okay, so here's the thing about gravitational potential energy. There is two different ways of looking at it. On Earth, we just look at things relative to Earth. And if you look at things in space, it's, so you know how, oh, we actually didn't cover this. Okay, so I'm gonna just write some equations real quick that just basically show you what I'm talking about. Okay, so you calculate Earth's potential energy on Earth via this formula, mgh. I'll actually go through this later, but that's how we calculate stuff on Earth. In terms of like the actual, like how it's actually calculated, it's g m over r. So these are the m's of the two objects. So this is the potential energy between two objects. So this is actually the same of like there's no like difference between the two, I guess. That's what I'm trying to say. It's dependent on the two masses, the masses of objects. The potential energy is going to be the same regardless where you are. Well, actually, yeah. Yeah. I don't know if there's a better way of explaining it.
You have gravitational potential energy, right, Mr.
Yeah.
Hu? Okay.
The gravitational potential energy is actually kind of messy when you start looking at things in space, because then you have to start accounting for it, because every single object will have gravitational potential. You'll sort of feel gravitational potential energy from any single object in space. So it gets really complicated really quickly, because then you can start like taking the integral of all of these. Like, if you don't know what integral is, it's basically you are accounting for every single contribution from every single object. It can get really messy really quickly. In terms of two objects, I mean, this is always true. The potential energy between two objects is g and m over r, where r is the distance between the two objects. And so the gravitational potential energy is dependent on the masses and the distance between the two. So if you're taking two equally massive things in space, the gravitational potential energy acting on each one of them would be the same. Yeah, that's the best way I can think of it. I can probably go into more in depth in this if you wanted, but it can get messy really quickly. That's why we're only focusing on gravitational potential energy on Earth. Gravitational potential energy in space, that's like a whole nother thing. Because also the force of gravity in space is also more complicated than just mg. So it's like if we look at things on Earth, it's simpler. Yeah. Okay, and also the stuff we do is it's sort of like a simplification. So here's the thing about physics is there's a lot of simplifications where you're looking at specific cases. So there's sort of like a, for example, a lot of the equations we're working with here, they're actually simplified versions of more like complex ones. But a lot of times you don't need to use the complex equations for a lot of scenarios. For example, like the force of gravity we use is a gross it's like not accurate because relativity is the most accurate way of describing gravity. But gravity in most of the time is like not practical, and then it's very messy. So we just use Newton's laws because those are good enough, essentially. So that's sort of how it works. So I don't know what I'm saying now, but yeah. Okay, going on a tangent, and I don't know what I'm saying. Okay, so chemical potential energy. Chemical potential energy is the energy stored in the molecules of materials. So basically, when you have materials, they're bonded in such a way that when you break down those bonds, it releases energy. So usually, like stuff like stuff in food, it's usually glucose. And so when you break down the bonds in glucose, it releases energy. When you have like a hydrocarbon, so like octane, propane, ethane, methane, all of those like hydrocarbons, they're all bonded in a way when you break them down, it releases a lot of energy. And so that's basically what chemical potential energy is. So gasoline is a good example of chemical potential energy because when you burn it, you can use that energy to do stuff essentially. The food we also provides our bodies with chemical potential energy. So in the chat, I can give me some examples of some fuels that have chemical potential energy. So what are some things that might have chemical potential energy? What's with everyone being obsessed with me today? Not that that's a bad thing. I think I'm really interesting, but
Mr. Who, you are an interesting guy.
that's good to know. That's good to know. Good to know. Solar energy. Solar energy would be an example of solar energy would be an example of radiant energy. Usually with chemical potential energy, we're thinking of like burning stuff essentially. So like burning food, burning like fuel, burning like potatoes are technically a good example of chemical potential energy. You're basically like burning stuff through like combustion, or your body's burning stuff through food. Yes, wood would be the good example of chemical potential energy. Yeah. Stars is no, stars would probably be more like nuclear energy, and that's different. We won't cover that, but stars is nuclear energy. Basically, oh gosh, it's gonna go up there. Yes, but yeah, that's a good idea. But stars are actually nuclear energy. Arson, wow, great. Okay, so this is the penultimate energy we're gonna cover. Elastic, which is like spring potential energy, and that's basically the potential energy that gets stored in an object when the object is being bent or stretched. So when you bend or you stretch an object, you are sort of storing the energy in the stretching of it. You're giving it tension. So when you're stretching an object, there's a lot of tension in the object, and so when you release it, all that tension gets converted into kinetic energy essentially. Basically, when you stretch an object, you're giving it elastic potential energy, and then when you release it, that gets converted into kinetic energy. That also works when the object is compressed. And so if you have like a spring or like a slinky, when you compress it, you're also giving it elastic potential energy, and then when you release it, all that kinetic potential energy gets turned into kinetic energy as well. So in the chat, I want you to give me an example of an object with an object with elastic potential energy. My car's suspension. So yes, technically, my car suspension would have elastic potential energy. A slinky. So I literally just said slinky, and then someone just said it, and that's like not very original. That one thing that's called plagiarism. That's called plagiarism, and that's not ideal. I also like keep doing this thing where I I'm a very like physically like aggressive person because I'm very, oh my God. See, I literally snapped the thing on like my mask like 3 times just now. And it's like very, very annoying. And this is what happens when you're too yoked. When you lift too much. Actually, I don't lift that much. I'm just pretending. But I just keep breaking all of these. How do you figure out when you will get potential energy and when you get a bent part? Oh gosh, if I didn't hear you. Okay. So how do you figure out when you will get potential energy and when we get a bent part? Ooh, that's good. That's a good question. I think it depends on whether or not. I guess this is like when it depends on like the. I think it sort of gets. I guess it sort of depends on like the maximum force that the object can withstand. So I guess like this is, I guess it's sort of an engineering thing where you sort of figure out like the maximum of force that the object can withstand, and so up to that. So like with a bridge, for example, right? Bridges will actually, and like buildings and stuff, they actually will flex and stuff. So they're not perfectly rigid. There is a sort of a breaking point though, when the amount of force being exerted on the bridge exceeds its capacity. So basically when you get a bent part, it's because the force you are applying to it is more than the force that it can withstand. So there's sort of like a mathematical force that it can withstand. How you do that? I'm not a material scientist, so I can't really answer that for you. But basically there's sort of like a threshold of forces that can work with the object. And then so when you apply more force than that, the object can't withstand that much force, and so it's going to break. So yeah, Slinky, someone just said Slinky another time. Gosh, you guys are like just stealing everything I say, or you're just citing me and everything. A rubber band, thank you for actually providing an original idea. A rubber band does have elastic potential energy. A mask does have elastic potential energy, except I keep breaking all of mine because I'm too strong. So yield strength. Yeah, I guess you can think of it as yield. You can't say Slinky twice in a row. That's just like, oh my God. Be original, please.
Hey,
Okay.
Being mean to students is actually plagiarism to every other teacher. So
Only if I reuse the same jokes. I'm really original with all of mine. So
Mr. Who, technically, if I say Slinky multiple times, it's not plagiarizing anyone because you only said it once. I said it twice.
yes, but it's about who said it first. That's what matters.
But I said it twice first.
Oh my
also we
God.
can democratically elect who we believe said it first.
Oh my
Facts
God.
can change.
Okay,
Yeah,
so
we
this is
should
what
vote for who should be a
all of
teacher
your
today.
This is what happens when you use all of your 2 brain cells to like.
I vote for
really, like,
myself
find a
to be
loophole in
teacher.
this versus just accepting the fact that I said it first. So disappointing. Someone just said Slinky. Someone just said Slinky again, and then they cited me this time. Great, thank you for citing me. But I want an MLA citation next time. I voted for. Oh my God. Oh my God. Okay. This is the last energy. Unless you want to keep hearing me talk forever. Okay. So the last kind of energy is electric potential energy. This is actually a very important energy. Unfortunately, we won't be doing a lot of this in our class, but this is something that's very important. If you go into college, or if you do decide to pursue if you do any sort of physics class at some point in your life other than this class, you will 100% use a lot of this electric potential energy. You will definitely use a lot of it. So basically, 2 charged objects will have either some attraction or repulsion from each other. Basically, and when you have these 2 objects, that sort of attraction and repulsion has potential energy, basically. So like charges they repel each other. So when you bring them together, you are effectively storing energy to do so, because you have to use energy to bring these like charges together. So you're storing energy to do so. When you release the 2 charges, those charges gets turned into motion. And so you're effectively like, that stored energy that came from you putting these 2 charged particles close together, they get released into kinetic energy. The other example is sort of like in a battery. So in a battery, what actually happens is you have positive and negative charges, but you're actually sort of separating the 2. You're basically one side of the battery, the positive side, basically most of the electrons from that are removed. A lot of the electrons from that are removed. The negative side, you have a bunch of extra electrons. So when you complete the circuit, so by separating these, so because then positive and negative charges, they want to be together. When you separate the 2, you are effectively using energy to do so. So you're effectively storing energy by separating the 2 charges away from each other. So when you connect the circuit, the 2 charges will want to go close together, and then all that stored energy gets turned into kinetic energy, or the energy that you want to use. So that's basically how a battery in a circuit works. You separate the 2, you separate positive and negative charges, and then when you connect the circuit, you have a flow of electrons from the negative side to the positive side, that actually creates electricity. So that's a very quick 5-second summary of how circuits and electricity works. We could do a whole unit on this for sure, but time-wise, we don't have that time. So basically, when you separate or bring together two charges, depending on the charges you have, you will require electric potential energy to do so. Okay. The last example of electricity, electric potential energy, is sort of with lightning. So what happens is the bottom of a storm cloud becomes negatively charged, and the ground becomes positively charged. And so what happens is the attraction of the two has a lot of electric potential energy. So there's going to be a ton of electrons that flow from the two ends, and so that creates lightning. So basically, the flow of electrons, because of the flow of electrons, will be caused by having electric potential energy. So I guess another way of thinking about potential energy in general is when you have a lot of potential energy, that's what we call high potential energy. High potential energy means you have a lot of potential to do stuff. You're ready to go. Low potential energy means you're done going. So you want to go from an area of high, you want to go from high potential to low potential. So yeah, so you want to go from high potential to low potential. So in general, if you want to think about things, you want to go from high potential energy to low potential energy. Lightning is electric potential energy, yeah, because basically you have a bunch of positive charges on the ground, and the storm cloud is a bunch of negative charges. So because you're sort of separating the two positives and the negative charges, there's going to be a lot of potential energy through this separation. So when that happens, all the electrons, they want to go from, because they have a lot of potential energy, they're going to want to go to the other side. Basically, yeah. Okay, so that is pretty much it for energy in terms of the energy types. So we have about 18 minutes left in class. So for the rest of
We should have a
today,
rap battle.
Yeah, rap battle
Okay.
between John and Mr. Who to see who said it first. Who said?
Okay. Oh my gosh. Okay, so let me go over what we're doing for next, and then you guys can decide if you want to rap battle me or something. Okay, so for the rest of the day, we are going to so I added a new section on Roller Coaster Tycoon that's called the energy section. Basically, your goal is to identify where all 8 types of energy can be found on your roller coaster. I believe that you can identify all 8 types on your roller coaster. If you're having trouble doing that, you can also try to identify them near your roller coaster. So maybe the pedestrian nearby might have some sort of energy that your roller coaster doesn't have, but you want to try to identify as many types of roller coaster energy on your roller coaster as possible. You're gonna have to look, try to identify all 8, and you're also gonna have to try to label it. You're gonna label it on your roller coaster where the energy can be found, and you're gonna sort of write out a very quick summary of why that energy can be found there. So that's what we're doing today for the rest of today, and then yeah, I'll let you get started, and then if you can, and then now you can debate whether or not you want to rap battle me or something. Apparently, it's very interesting.
Do you want us to submit the energy graphic organizer?
Yes, when you finish it, you can submit it. Yeah.
I can't find the roller coaster tycoon energy section. Can you post it in the chat, Mr. Hu? Thank you.
Okay, so we are out of time here. So I'm gonna start wrapping up. So first things first. First period was supposed to be my wild period, but you guys have surpassed that now. So I don't know if that's good or bad, but that's definitely true.
Nice.
Also, another note. Apparently, someone in my first period was telling me that apparently Miss Shepard's apes class has the wildest chat of all time. Now, I'm a very competitive person. But I'm a little upset that our chat was not the wildest one, apparently, of all time. So that's our goal, is to be the wildest class on campus. I need to establish a notorious reputation here. But anyways, you're welcome. Thank you, much appreciated. Okay, so what's that? What am I? Okay, so no homework. We're gonna continue everything. No homework. We're going to continue everything next week. So yeah, if you want to try to get caught up, that's definitely a good idea. Also, for those of you seniors, guess who is going to be chaperoning prom today? Yours truly. You can't escape me even if you try. So that's it for today. I will see you guys all later. You can't
Bye. Have a
escape
nice week.
if
Bye,
you
thank you.
tried. I'm going to be all over there.
Thanks,
Just
Mr.
like
Lee.
I'm going to just